Hello students, today we're going to continue with the topic of waves. In particular, we're going to look at crests, troughs, speed of waves through a medium, and what type of things affect the speed of a disturbance through that said medium. Now, before we begin, let's make sure that we understand our terms from the last video. When we're talking about a medium, anytime you hear the term medium, it can be anything that a wave is going to be traveling through. So it could be water, it could be air, it could be some sort of metal. It can be pretty much anything that you're coming across, all right? Something that a pulse or some energy is going to travel through. Now, there are some waves that do not require a medium, and that would be, let's say, electromagnetic waves. You don't have to have a medium, a material in outer space for sunlight to travel through outer space from the sun to the earth. All right, so mediums that require or waves that require a medium, those would be mechanical waves. And those are the ones that we're going to talk about for the most part today. All right. So let's take the one in terms of water. So here we have our medium. We're going to talk about some water. And the example that we're going to use is we're going to use a bird sitting on top of a rock or a post in the water. If that water is nice and still, it's not moving up and down at all, there's no disturbances, we would say that wave is in an equilibrium or a rest position, right? So anything before you have some sort of disturbance is going to be in equilibrium. It doesn't have to be water. I said, when we're looking at waves, it can be traveling through any type of medium. So maybe instead of it being a water wave, maybe it's a kid that's sitting on a swing. This is my hideous example of a kid sitting on a swing. All right. So if a kid is sitting on a swing right now, the kid isn't moving. So this kid is in an equilibrium, right, at a resting position. So it's not real fun if you're sitting on a swing and you're not moving around. You need to have some motion. You need to have somebody push you. Well, if somebody's going to push you on the swing, they're going to apply a force onto you. There's going to be a disturbance, and you're going to start swinging back and forth, right? In the terms of the water, well, if you have some wind that starts blowing over top of the surface of the water and it causes a disturbance, now the water wave is going to start moving up and down like this. All right, so you have a disturbance. That water is going to be moving or oscillating back and forth. So any of our oscillators that we're talking about, we just have some motion of a back and forth movement. So I'm just going to put in here back and forth. All right, so we have some sort of back and forth movement, whether it be in the terms of the water going up and down or the swing moving left and right. It can really be anything. It could be, heck, it could be even you taking a wet towel and you snapping somebody with it. You provide some sort of motion at your hand with the towel. That energy is transferred through the towel and whack, you smack somebody with it. All right, so another term, we have a cycle. A cycle is one repetition. All right, so in terms of this kid over on the right, this kid moving forwards, then backwards, that is one back and forth movement. All right, now if we are going to time how much time it takes for that kid to swing to the right and then come back, that time frame for the kid to move from right to left, that is the period. So I'm going to put in here time for one. I'm going to put oscillation or one cycle to occur. In the terms of our water wave, one up and down motion. So if we had a little bobber sitting here, we're going to go fishing now. If that bobber moves up down, and then back to that original position, that amount of time for that bobber to go up, down, and back again, that is 1 period. All right, we're describing this oscillation. We have this object that's moving back and forth, back and forth. Well, we usually don't just time one oscillation, one cycle to occur. We don't do that, because if you were going to look at a guitar string vibrating back and forth one time, you're not going to be able to be fast enough on your stopwatch to stop or start and stop that. It's vibrating much, much too fast for you to take and to visually see that string move back and forth and for you to time it. It's just not going to happen. So instead, what we can do is we can look at the frequency. The frequency would be our number of vibrations per second. Right? So if our guitar string, if it's going to be vibrating back and forth several hundred times per second, what we can do is we can say that if it vibrates back and forth 100 vibrations, that's supposed to be VIB. Okay, if it's going to vibrate back and forth at 100 vibrations per 1 second, then we can say that our guitar string would have 100 hertz associated with it. So our term for this vibrations per second, or our frequency, is going to be hertz. Now, it's not H-U-R-T, it's H-E-R-T-Z, hertz. And then the last thing when we're talking about topics or terms that we had from the last video, we talked about amplitude. An amplitude is how far off of our rest position. So this little dashed line right here, that's the water before we had any disturbance with it. So our amplitude is how far down or how far up is that water wave going to be. Now in this case, when we're measuring that displacement, all right, so I'll put displacement of medium. If we have our displacement of our medium, we might measure this in terms of centimeters, but how are you going to measure your displacement when it comes to something like a pendulum? Well, a pendulum, what we would do here is we would figure out what is our degrees. So this would be our degrees. So I don't know, I'm going to say that that's a 35-degree angle. So it'd be 35 degrees. So there's a couple different ways that we can measure our amplitude, whether it be degrees off of equilibrium or number of centimeters off of equilibrium. We had some formulas that we looked at also. Our formulas, when we're trying to calculate the period, now our unit that we used for period was a T. All right, so our period is T, and we said that that equaled 1 over the frequency. And then vice versa, if we're trying to find the frequency of our waves, the number of vibrations per second, we would say frequency equals 1 over the period. All right. And you had a couple of story problems related to that, and hopefully you understood those. If not, we will be coming back to that shortly at the end of this video. Okay, let's go on. So what exactly is a wave? As I said, a wave is an oscillation. An oscillation, don't get that term confused. All we're talking about with an oscillation is an up and down motion. All right, or a back and forth motion. So we have something that's moving up and down. I do want, in your notes, I do want to see that term. Okay, so an oscillation. Well, if we're looking at what an oscillation does, in the terms of a water wave, what you should see is as you cause a disturbance in water that's at rest, you're going to notice that that water wave is going to propagate or move away from the point of origin in all directions. Now, that's not true just for water waves if you're looking at sound waves as well. Sound waves propagate or move away from the source in all directions at the same time. Right? Now, where that idea of this sound wave or water wave propagating away from its source, how we can use that idea is the Doppler effect. The Doppler effect, when you have, let's say, a car that's going to be traveling past you, you've probably heard of this before. You're on the side of, that is my beautiful car right there. The car is producing a noise. Now that circle is that sound wave propagating away from the car. Now if the car is sitting still, all of those waves are equally distributed apart. Right? That's the wavelength of our sound. But what happens when our car moves forward? Well, when our car moves forward, we don't see this. We don't see that. Because see, if your car is producing sound and these waves are moving in this direction away from the car, if you start driving your car towards where those waves are propagating to or moving to, what's going to happen is we're going to have a distortion here. It's going to look more, I don't want to do quite like that. It's going to look more like this right here because we're moving towards that wave. So now as the car is moving to the right here, it's moving towards where those sound waves are going. And what that actually does is that produces a high pitch. Right? So when you're on the side of the road and you hear, you get that high-pitched noise because these waves, these disturbances are closer together. And then back here, those are more spread apart. So what you do is you get a low pitch right here. All right. So I'm getting off topic here, but we're looking at oscillation. Oscillation, we have waves that are being produced. Okay. What are parts of our waves? Well, if our wave is that water wave and our bird is sitting on the perch, and let me put my bird in here. Here we go. So if I have my bird and he's sitting on this perch here, and these water waves are starting to come through. Oh, my bird doesn't want to cooperate with me. I'll make him smaller. Oop, there we go. And if our bird is watching this disturbance, and I do want these things written down in your notes. So all three of those are what you need to have written down. So as this bird is watching these waves, we can imagine that our equilibrium or our rest position is this dashed line right here. So that's our equilibrium. Our crest is going to be the highest point of the wave. So the greatest amplitude up off of that equilibrium would be our crest. And then a trough, I mean, this isn't a hard thing to understand. If you're talking about a trough for like a pig, the trough goes down into a valley. So here, the lowest point, we have our trough, the low point. All right. Now we're going to continue. You got to make sure that you know what those two terms are because we're going to use those terms to help us identify our wavelength and a few other things in terms of energy. When you're looking at amplitude, does amplitude have anything to do with the speed of our waves? So if I'm whispering or I'm yelling, does that change the speed of the wave at all? No, it doesn't. Amplitude, whether you have a person talking softly or a person that's yelling at the top of their lungs, the speed at which that sound is traveling is the exact same for that particular medium. So if you're in your classroom, your bedroom, outside, and as long as we don't change the temperature of the air, change the humidity of the air, the speed of sound is going to be the same for every single person around you. All right. So We have the next part. We have the frequency of the wave. The frequency of the wave, I'll make sure you get this written down. When we're looking at the frequency, it's the rate at which every point on the wave moves up and down. All right, now that means how often is this thing moving? We had the bobber. That bobber is going to be moving up and then down. That would constitute, if we're just looking at one up and down motion, what's our term for that? A cycle, one cycle. If you need to pause the video at any point in time to write your stuff down, go ahead and do that. We have the amplitude. One more time, just repeating ourselves. The amplitude is going to help to identify the amount of energy that's going to be traveling through that wave. I want that definition written down here. All right, so it relates to the amount of energy that's being transferred through. We're going to find that just because we double the amplitude, that doesn't mean the energy is going to be doubled. All right, that's not the case. All right, and in a later video, we're going to look at how much more energy is associated with the wave if we double the amplitude. You might be surprised. Okay, our parts of our wave. Now our new stuff here. What exactly is a wavelength? Well, I want you to have this written down in your notes here. A wavelength is the distance from any point on a wave to the same point on the next cycle of that wave. So they have to be consecutive points. That means when I say consecutive points, we can't say that we're going to measure from the crest of one cycle to the trough of another. You can't do that. It needs to be consecutive points. So if I start my wavelength, and wavelength is a distance. So this guy right here, this is a distance that we're going to measure. So I start my measurement for my distance at the top of that crest. Well, if we look at our down, back, and up motion, that completes one cycle. That's one wavelength. Now that one wavelength, it doesn't matter as long as we don't have any secondary wave interfering with this where we could have constructive or destructive interference. Our wave is going to be the same at any point in time. So if I take this image here and I move this over, you see how it's the exact same thing? If I were to go, if I had another one over here, we'd see the exact same thing here. So what happens, though, if I take this image, all right, and then I want to instead measure that from the, let's say from the, we'll go from the what's called the node, or the area where in which there is no displacement here. All right, so watch what I do here. I'm going to take this one cycle. I need to go up, okay, and then I need to go back down. We'll go down and then back up. All right, now those parts constitute one wavelength. All right, and if I grab this image and I put this anywhere else, see how it's the exact same thing. It's the exact same thing. No matter where I start that and finish that, it's going to be the exact same length. Well, what happens if I don't want to start at the node? Let's say I want to start at the trough of it instead. Will that change my wavelength? All right, now I purposefully broke this up into those parts. That way I could grab my image and put them in different places. So let's say if I start at the node and I move down first. All right, so I'm just going to move my pieces. I may not be perfect because I didn't draw them perfectly or sketch them perfectly, but do you see? I started at the node, and where did I finish at? At the next consecutive node. All right, well, how about if I take that image and instead of starting there, let's say if I want to start, let's say I want to start at the trough like this. Well, if I want to go there, I grab this piece, there's that one, and then I can go here, and then I can go there. Bam, see? They're all the exact same thing. So no matter what you're doing on a wave, as long as you're going from one crest to the next consecutive crest, you're doing it correctly. Now, our unit of measurement that we're going to use meters as the base unit. So whenever you're measuring wavelength, the Greek symbol for wavelength is lambda, and we're going to measure that in terms of meters. Okay, even if you have it measured off in centimeters, I want you to convert it to meters. All right, we're going to use meters per second in just a little bit when we talk about the speed of something. Okay? All right. To reiterate, we have crests, high points, trough, low points, and then our wavelengths. It can be any two consecutive points on our wave. So we just measured up our distance. All right, that's the wavelength. The wavelength is our distance. I talked about the time for one oscillation at the beginning. If you remember back to the kinematic stuff, speed equals distance divided by time. Well, distance divided by time, I have what is my wavelength. So what's my distance from this point right here down and back up? Well, that's my wavelength. My wavelength is my distance that I'm measuring. If I'm trying to figure out how much time it takes for one cycle to complete itself, that's the period. So I have figured out the velocity of my wave by dividing wavelength by the period. And I want to make sure that you have this written down right here. A wave moves one wavelength in each cycle. All right, and then we're going to put right here. It says, since a cycle takes one period, the speed of our wavelength is divided by the period. All right, and we're going to make sure that you have that formula written down because you're going to have to use that when we get to the story problems at the end. Let's go on to the next thing. The speed of waves. The speed of a wave is not how fast the wave spreads. Okay, that's not the case. That's not how fast this, or I'm going to make sure I read this correctly. That's not how fast the water surface moves up and down. All right, I need to make sure you understand that. When we're talking about how fast a wave spreads, you're looking at the distance between those whatever 2 points that you're looking at. All right, so if we're looking at, let's say, just one cycle, so from here to here, we would measure that, and we'd have to use this distance divided by whatever time it would take to cover that part. Okay? Well, let's say that you can't measure something that small. So what could you do instead? What could you do instead is you could look at how many vibrations are occurring per unit of time. So you could look at how many vibrations are occurring between these 2 points. So you'd have one up and down, you'd have two, you'd have 3, 4, 5, 6. So you'd have 6 hertz or 6 vibrations, and that frequency could be used to determine how fast your wave is. Now you might be thinking, wait a minute, that frequency isn't in here. But if you recall from the last unit, what can we get from the frequency? Well, we can say that the period equals 1 over the frequency. So we've got to keep our formula sheet ready so that way we can relate these terms together. All right? So the speed of our wave, make sure you have this down. The speed is the distance traveled. Okay, now that distance traveled, it could be our one cycle. It could be just one wavelength, or we could, figure out what our frequency is, and then determine what our period is from that. So we have the speed is the distance traveled, one wavelength, divided by the time it takes for one period. So our formula, why don't you have this whole thing written down here? Speed equals distance divided by time, nothing new. We have wavelength divided by period, distance, wavelength, these two are the same, okay? And we're going to use that Greek symbol lambda for wavelength, all right? So make sure you know what that symbol means. Equals 1 over the period, all right? So 1 over the period. Now, why did I have 1 over the period? Because if we just separate, let me do this. If we separate this into wavelength times 1 over period, what that allows us to do is it allows us to throw the frequency into the formula so that way we can relate terms. All right, now, if you're feeling a little overwhelmed by the formulas, once we start working them out, I think it'll come together for you. All right, so our formulas, you should have this written down. Now, our units of measurement, if you struggle sometimes remembering what each unit is, maybe write these down. You have speed. Speed equals meters per second. I said we're going to use that term meters, or that unit of measurement meters. We're going to use seconds. All right, we're not going to use centimeters, or we're going to try to not use centimeters. If you're looking at wavelength of light, you're kind of stuck. Yes, you could change them around, but it's so much easier to say 630 nanometers. Okay. Anyways, I'm getting sidetracked again. Let's look at frequency. Frequency. What's our unit for that? If you see hertz, you know you're looking at frequency. If you see meters, you're looking at wavelength. If you see seconds, you're looking at the period. All right. Know the units of measurement and have a good formula sheet ready so that way you don't get struggling. Our first example here, it says the wavelength of a wave on a string is 1 meter and its speed is 5 meters per second. Calculate the frequency and the period of our wave. All right, so it says that we need to calculate the frequency and the period. I know that our speed equals distance divided by time, all right? And along those lines, if we're looking at our, let's say our other way that we could do this, you could have the, let's see, our frequency times our wavelength. There we go. So we just throw our numbers in here. If we throw our numbers in, you've got 5 meters per second. 5 meters per second equals, we have 1 meter. Meter is measuring wavelength, so 1 over t. Oh, I can try to figure out what my t is now. I have, we multiply by t, divide by 5, so t equals 1 divided by 5 meters per second. There we go. If we look at the other one, you've got 5 meters per second equals, well, I don't know the frequency, but I do know the wavelength is 1. So if I want to figure that out, my frequency for this one, I'd have F equals 5 meters per second divided by 1. So my frequency would be 5 hertz or 5 vibrations per second. And then our period, if we had to do the numbers of that, you'd have 1 divided by 5, so 0.2, is it 0.2? Yeah, okay. So this is just another example. We're going to do plenty of them in just a little bit. But before we get on to solving some of these, let me jump back to what I said at the very beginning. All right, the speed of a wave does not depend upon the source of your wave. If you have a person with a high-pitched, squeaky voice, and then you have a person with a very low, bassy tone to them, when they start talking, you don't hear if they both start talking at the exact same time, you don't hear the high-pitched, squeaky person first, and then moments later, you hear the person with the deep voice. If they both speak at the same time, you will hear both of them at the exact same time. Now, if you don't believe that, you could try it yourself, or what you could do is take that idea that the source of our wave is not going to determine the speed, and look at different colors. Turn off your lights in your room or close your eyes and then open them. Red light has a longer wavelength on it. And then if you look at blue light, it has a shorter wavelength. So the type of frequency or the wavelength, it's not going to matter. The tone of the person, it's not going to matter. It's the material through which that wave is traveling that's going to determine the speed of your wave. All right? And I have on the right-hand side over here some examples of it. If you're looking at air, nice cold air, it's at the freezing point. How fast is the speed of sound when you're trying to get somebody to measure how fast it is? Well, if the air outside is 32 degrees Fahrenheit, sound is going to travel at 1,087 feet per second for every single person. Anything dropped and hits the ground and you hear it, that's how fast it's going to travel. Now, if you warm that air up, you're going to change the density of that air. If you change the density of the air, then you're going to change the speed at which sound is going to travel. So it's going to increase by well, not quite 100, but it's going to be 1,127. Let's say we take air, which air is spread out. It's not, those particles aren't constantly in contact with one another. But aluminum, those particles, those atoms of aluminum, they're tightly packed together, more tightly packed together than what air is. It's a solid. Aluminum is a solid. So if those particles are closer together, they're going to be able to transmit the energy or transfer the energy from one atom to the next at a faster rate. So you're looking at 16 times faster. So instead of 1,000, you're looking at 16,700 feet per second. So if you look at, you can take a look through these other ones and see what the examples are. But the denser the material, the faster that wave is actually going to travel through it. So I want this definitely written down. The density of a medium, the more dense you are, the faster, the more dense you are. The more dense the material is, the faster that wave is going to travel. All right. A good way to see this is if you're talking and you want to test and see if sound travels faster, put your ear on your desktop and then have somebody tap it, or if you have the strings with cups and you want to transfer the energy, that way you can test it out that way as well. Okay. Now, let's get on to our story problems here. Now, the story problems, this, you need to show you all your work in order to get the credit for this. You have the speed of our wave. It's the same formula we had before. Frequency, hertz, wavelength, lambda, meters. And then what you don't see is period, time. All right. But I'll help you answer a couple of these questions, and you're going to be on your own for the rest. We have on the graphic at the right, it says on the graphic at right, label the following parts of your wave. You have to label one wavelength. I don't care where you start that one wavelength. You can start at the crest. You could start at the trough. You could start at the node. It doesn't matter. But you have to represent one wavelength. So if I start here, I need to go up, down, and back again. That's one wavelength. All right? So I've done that part. What you have to do is you now have to label up the other parts. You have to have half of a wavelength. And then you need to label The amplitude, you need to label the crest and you need to label the trough. All right, so you have to label each one of these. I'm going to put right here, one wave. You know what? I'm going to do this. One wavelength. All right, so one wavelength is that orange. Once you have those labeled, it says part A, how many wavelengths are represented in this particular diagram? Well, if this is one wavelength, how many wavelengths do we have? Okay. It says letter B, what is the amplitude of the wave shown? Well, how many centimeters up off of the equilibrium is that? Let's go to the next part. The next part. This is making sure you know how to draw your waves. So we have our equilibrium is 0. And I'm going to say that this is 1 centimeter and this is 2 centimeters here. Then we go downwards. This is negative 1 centimeter, negative 2 centimeters. And if we draw this out, again, it doesn't matter if you start at the node or antinode. It does not matter. You just have to make sure that your wave has an amplitude of 1 and the wavelength is 2 centimeters. So personally, what I would do is I'm going to go like this. We're going to go 1, 2, 3, 4. So I'm going to say that my wave is going to go like this. So I'm going to go 1, 2, 3, 4. It's going to go down like that. We're going to go 1, 2, 3, 4. So negative 2. We're going to go 1, 2, 3, 4. So I'm going to have one wavelength is what I'm going to squeeze in here. Okay. And then to label this correctly, if it's 2 centimeters, I'm just going to put up at the top right here, 2 centimeters. Pretty easy, right? Okay. Down below here. Now you have to do the other one. Number 3. Remember those different formulas. All right. So I'll write them up here. Hopefully you have those written down. We have velocity is lambda divided by t. And then we have velocity equals wavelength times frequency like this. All right. Says a water wave has a frequency. All right. So frequency, right? It has a wavelength of 5 meters, 5 meters, wavelength 5. It says calculate the speed. Well, that's the formula I have to use because those are the variables that I had. So I want to see on your paper 2 hertz times 5 meters equals a speed of, and I'm running out of space here, 10 meter per second. Okay. Let's go down to, let's say number 7 here. Number 7, and I want these on a separate piece of paper. I don't want them squeezed in on this. I want to see the work. So number 7, we'll get rid of these highlights here. Okay. Says a sound wave travels at 330 meter per second. Well, that's velocity. And it has a wavelength of 2 meters. So wavelength, 2 meters. It says calculate the frequency, and it says calculate the period. All right, well, you got your 2 formulas. We'll just have to take your velocity, 330 meter per second, and in order to solve for the frequency, I'm going to divide both sides by the wavelength. So we'll divide that by your 2 meters. So this would be 100 and what do we got? 100 and cheesy Pete. Why am I having troubles? We have 150, 165, is it? I'm pretty sure that is. I don't want to just guess. We have divided by 2. Yeah, 165. So 165 and our frequency is, you could either write it as vibrations per second, or remember you could write it out as hertz. Okay. That's the first part of this. That's the frequency. And then the period, you have 330 meter per second equals, and then you have the wavelength. What was our wavelength again? 2 meters? 2 meters divided by the period. All right. So Here is where you have to multiply both sides by t and then divide both sides by 330. So I'm going to move this guy over, I'll move this guy under. Okay, right like that. So 2 divided by 330, I'm not going to try to do that in my head. 2 divided by 330, we have our period, the amount of time is going to be 0.006 seconds for one vibration to occur. Okay? So what you have to do is answer up the rest of these questions, take a picture of your work, submit that to Schoology. If you have questions, make sure, as always, you get a hold of me. Don't turn something in that has just bogus numbers. You won't get credit for it, all right? You have to show your work, and you have to ask questions if you're not clear on how to do something, okay? Pretty straightforward stuff. If you need anything else, let me know. Okay? Later.